Okay, let's continue our study. We've already finished section 4.6. We will skip the section 4.7. We'll jump to the chapter 5. Chapter 5 is called Series Representations for Analytic Functions. Okay, series representations for analytic functions. The first section, 5.1, sequences and series. So this section is very similar to the section, the corresponding section in the calculus, except here we are talking about complex numbers. The absolute value is a modulus of a complex number. But still, let's set up the language. So first definition, definition 1, a series is a formal expression of the form C0 plus C1 plus C2 plus C dot dot dot. Or equivalently, here is a complete writing, not complete, just a long form. Or equivalently, we write it in a sigma notation, j from 0 to infinity, Cj. In the calculus, we always start from C1, C2, C3. We start from C1. Here we start from C0. It's because later we are going to apply this theory to the Taylor series. And in the Taylor series, C0 corresponds to the constant term. Yeah, constant term. So that's why C0, the zeroth order, the constant term. It doesn't matter what index you start from. So where the terms Cj, where the terms Cj are complex numbers. Okay. Then this is just a formal writing. We don't guarantee it is a number. It represents number or not. So the nth term, nth partial sum, sorry, not nth term, nth partial sum of the series usually denoted by Sn is the sum of the first n plus 1 terms. You see here, this is a interesting shift. Again, we are going to apply our theory to the Taylor series, the series representation of analytic functions. So here, this n actually means we cut the Taylor series up to degree n. Degree n plus the constant term has n plus 1 terms. So nth partial sum has n plus 1 terms. That's a small difference. i.e., our Sn is sum from 0 to n. You see here you see the n, Cj. J is from 0 to n Cj. You have n plus 1 terms. And Sn is always a number because you have finite, you have sum of finitely many numbers. Okay, so if the sequence, so for each n you have a first partial sum, second partial sum, third partial sum, so you construct a sequence. The sequence of partial sums we write the Sn, n from 1 to infinity. The sequence of partial sums, okay, n from 0, 0, yeah, has a limit s. If it has a limit s, then the series is said to converge or sum to S. Okay, when you have a sequence in a complex space may or may not have a limit. If it has a limit, then we say the original series, sigma notation, infinite sigma notation, the series converges to S or sums to S. And we write S equal to the series J from 0 to infinity Cj. Okay. The sigma, a series that does not converge is said to diverge. Okay, if it does not converge, it is divergent. Okay. Okay, it diverges. Clearly, we know one series converge. Remember that we have 1/2, 1/4, 1/8, 1/16. Every time you multiply by 1/2, every 1/32, and so on. We have that geometric proof. Every time you cut into half, cut into half, cut into half, cut into half. So when you go through this complete process, you cover the whole square. Square is 1 by 1. So it's a half, 1/4, 1/8, 1/16, 1/13. Right. This is equal to 1. Or the series sums to 1. Okay. And this is a special example of a so-called geometric series. The geometric series. So lemma, the series sigma j from 0 to infinity Cj converges to 1/1 minus C if ops value of C is less than 1. So here I just want to use the picture to demonstrate the sum, so I didn't include 1. When J is 0, C to 0 is a 1, so I didn't include 1, but it doesn't bother if it converge or diverge. It bothers the value, but it does not bother converge or diverge property. Okay, so the lemma says, lemma 1 says this series always converge to 1/1 minus C if the ops value of C is less than 1. Okay. Well, let's see the proof. The proof is in the factorization technically. We know that 1 minus C to n plus 1 is 1 minus C, and 1 plus C to n. Okay, so from this factorization we get this is exactly Sn, so it's 1 minus C times Sn, the nth term, nth partial sum. So Sn is 1 minus C to n plus 1 over 1 minus C. And if ops value of C is less than 1, then we know the limit when n approaches infinity, ops value of C to n is equal to 0. right? When you have this real number less than 1, then it's nth power approaches 0. Then this is equivalent to c to n approaches 0. C to n approaches 0. Okay, it's a special property about the 0. If you replace this 0 by any other non-zero number, then it's not correct. Okay, c to n approaches 0. Here, c to n plus 1, it doesn't matter. So the limit of Sn is the limit approaches infinity 1 minus to n plus 1 over 1 minus c. This term approaches 0, so it approaches 1 minus c. 1 over 1 minus c. So that's the limit of the partial sum sequence by the definition. Sigma j from 0 to infinity, cj's power is 1 over 1 minus c. Here, this condition is used to guarantee the limit exists and is equal to 0. Right? Yeah. What is the standard proof? This series is called the geometric series. The geometric series is a very, very important and simple example of a convergent series. Because it's a very standard, it's very simple and very standard. So we want to always compare it with other things. And before we compare it, we have to know so-called the comparison test. So we want to compare, we have to have some tools. It's a comparison test. The comparison test says, suppose that the terms Cj satisfy the inequality of value of Cj is less than or equal to m sub j for all integers j, for all the indices j. Possibly it's not always correct for start from 0. So we say larger than some number capital J. So we can say that this language, or we can say that this inequality holds for integers except possibly finitely many. So larger than some number j is index j, or we say that except possibly for finitely many. Maybe like this inequality does not hold for C0, C2, C11, C million. Except those finite and many exceptions, this inequality always holds. That's equivalent to the to this statement. Okay, then if the series Mj, j from 0 to infinity converges so does the series of Cj. Okay, so the comparison test means if you already have a convergent series, and you just compare it with the convergent series. If if your series is smaller than the convergent series term by term, then your series also converges. Okay, so that's the comparison test. The proof is a standard proof. When you study the calculus, you have the same proof. just understand the number as a complex numbers, ops value as a modulus. Okay. Let's see the example. We're not going to prove it. So the example show that the series (3 plus 2i over j plus 1 to j's power, j from 0 to infinity. 3 plus 2i, it's a complex number. J plus 1 to j's power, this is a real, it is integers. Okay, so the total is a complex number. Converges. We want to show this series converges. Let's see. So the ops value of 3 plus 2i is square root of 9 plus 4 square root of 13. Square root of 13 is less than 4. And so the 3 plus 2i, the Cj, j plus 1 to j's power, its ops value is less than 4 over j plus 1 to j's power. And j is a 0, 1, 2, 3. Let's assume j is greater than 1. If j is greater than or equal to 1, let's just skip the first term. If j is greater than or equal to 1, then this will be less than or equal to 1. 1 plus 1 is 2. It's a 2 to j. 4 over 2 to j. 4 over 2 to j, if you want, you can write like the 1 over 2 to j minus 2. Okay? And this one is still a geometric series. It is still a geometric series. We know that this is a geometric series with common ratio (1 over 2). 1 over 2 is less than 1, right? We know that 1 over 2 is less than 1. So it converges. This is our MJ. Series MJ convergence by the comparison test. That series 3 plus 2i over j plus 1 to j's power, j from 0 to infinity, converges. And this part, we use that this inequality only holds for j starting from 1. It does not hold for j equal to 0. Right? Okay. After comparison test, in the calculus, we also have the ratio test. The ratio test. The ratio test is the following. Remember that the geometric series, what is geometric series? It's a r to n minus 1, n from 1 to infinity. This is a geometric series. If you put a 0 here, this is a r to n. Okay, let's start from 0. It's a geometric series. Geometric series, the next term is a times r to n minus n plus 1, a times r to n plus 1. The current term is a times r to n, then the ratio is r. We know that the ratio is less than 1, converges. The ratio is greater than 1, diverges. check greater than or equal to 1, both diverges, except A, of course, here we assume A is not 0. Okay, so this is the geometric series. They have the fixed ratio, the common ratio. And for the ratio test, suppose that the terms of the series Cj from 0 to infinity Cj have the property that the ratio, you see, the next term Cj plus 1 over Cj, they're complex, so let's put a opposite value, approach a limit L. So instead of have this fixed ratio R, they assume this this ratio approach to some limit L. The limit L is like this R as J approach infinity. Then we know that when R is less than 1, converge. R is greater than 1. In this case, we have to remove the equal sign. So then the series converges if L is less than 1 and diverges if L is greater than 1. Because you replace this fixed ratio by the limit, so you lose the property when the ratio is equal to 1. You lose that property because of you have a weaker condition. Okay. Okay, again, this proof is very, very similar to the proof in the calculus, so we're not going to repeat this. And let's see the example. Example to apply it. And be careful, it's always the next term over current term. J plus 1's term over J's term. Always this way. Future over current. So show that the series sigma j from 0 to infinity 4 to j and j factorial converges. So you see here, in order to get a ratio, you have to simplify the ratio. To simplify ratio, it's better to have a product instead of a sum, right? Each term you have a lot of product that you can cancel. If you have a sum, it's difficult to cancel. So this problem, this type of example, is like the essential example for this ratio test. So the j plus 1's term J's term and compute the limit J approaching. Because this is always positive number, this is a calculus example. It's a positive number, so we don't have to put opposite value. You simplify this ratio, you will get this is actually 4 over J plus 1. Most of the terms are cancelled. 4 over J plus 1. As J approaches infinity, of course, this limit is 0. This limit is 0, less than 1. So by ratio test, the series converges. Okay, so the series converges. Okay. In the calculus, we have a convergent series. We also have so-called absolutely convergent series. So, a series is said to be absolutely convergent if the series, the other series, if the series with ops value of Cj converges. Okay, so absolutely converges if the second series with all ops value converges, and we have the result that any absolutely convergent series converges. Right? Any absolutely convergent series converges. This is actually comes from the comparison geometric, the triangle inequality. Okay. And then let's see next. So the example is the following. We fix a z0. Of course, z0. Let's choose it's not 0. Fix z0 not equal to 0. Show that the series sigma j from 0 to infinity z over z0 to j's power converges for ops value of z less than z0. Okay. So here we still use that well-known factorization stuff. The thing is that let me read. Yes, we still use that. If you have 1 minus z over z0 and 1 minus z over, this is to nth power. Here's a this n plus 1. 1 minus z over z0 to n plus 1's power over 1 minus z over z0. It's a 1 plus z over z0 plus z over z0 to nth power. Okay. What is the purpose for this? So we know that if ops value of z is less than ops value of z0, then this z over z0 ops value to n plus 1's power, the limit approaches infinity. This will become 0. So this implies the series j from 0 to infinity z over z0 to nth power converges to the, when you take limit, this term disappears to the 1 over 1 minus z over z0. Okay, so it does not give any new stuff. It's just a geometric series. Okay, so here is the difference. What the author tries to explain is the following. Assume we have this a sequence of functions. So we have capital Fn of x, capital Fn of x as nth power of x, x twin, it's x twin, and we just focus on the interval 0 and 1, 0, 1. Okay, so here's a 1, here's a 1, excluding. We don't want 1. Okay. This is a graph of a y equal to x, and if you draw it, it's a graph y equal to x squared, and y equal to x cubed, y equal to x to 4th power, 5th power, and in the book you have a lot of pictures, so possibly this is y equal to x to 40th power, whatever. You just know that it will be more and more flat, and when it reaches 1, approaches 1, it will be very steep. It will be very steep. So when you have the point-wise convergence, you see here every point, you choose a point, for example, you have r, then r to nth power, the limit, it is always equal to 0. It's always equal to 0 for every point. But the speed is very different. When r is approach to 1, the speed approach to 0 is very slow. When r is equal to 0, the speed, the vertical limit approach to 0, this is very fast. They have totally different speed. So we say the convergence, the sequence of function fn convergence to 0 point-wise. For every point, it will converge to 0, but not uniform. They have totally different uncontrolled speed, so that's the uniform. It's not uniform. It's point-wise, but not uniform. Okay, so in order to apply the series theory, we need this one more definition, the uniform convergence. The uniform convergence is about a sequence of the series of functions or sequence of functions. Yeah, let's first study function. Sequence of functions. So the sequence of functions capital Fn of z, capital Fn of z, n from 1 to infinity, is said to converge uniformly to capital F of x on the set L. Is this L? I guess this is S. On the set of S, if for any epsilon greater than 0, there exists an integer n such that when n is greater than capital N, Fn of z minus f of z, F's value, is less than epsilon for all z in S, for all z in S. Okay. So first you defined for the sequence, and then after you have the sequence uniform convergence, the series the series, sorry, it's not sigma, the series fj zj from 0 to infinity converges uniformly to fz in S if the sequence of its partial sum converges uniformly to f of z. Okay, so whenever we talk about the convergence of the series, it's always the convergence of the partial sum, right? Okay. Let's check here. In the previous computation, this place, the reason we introduced or we discussed this example is the following. Remember here, we have the limit z over z0, ops value to n plus 1's power is equal to 0. So for epsilon greater than 0, there exists capital N such that for n greater than capital N, the ops value is less than epsilon. So this is the epsilon n language for this convergent sequence. But this capital N, here, if you want to make it clear, the capital N, of course, depends on epsilon. The capital N also depends on Z. For Z very close to Z0, this number is close to 1. When it is close to 1, you need a bigger N. If Z is close to 0, then Z over Z0 is very close to 0. Then you don't need a big N to satisfy it. You need a small N. So let me write it down here. That's an example. For this series, and of course we require this condition. Given epsilon greater than 0, there exists capital N. Here, let's emphasize capital N depends on Z, depends on epsilon, such that for all n greater than capital N, difference is less than epsilon. So this is the definition. And if Z is close to Z0, NZ epsilon has to be bigger, has to be larger. If Z is close to 0, not Z0, is close to 0, then n of Z epsilon can be smaller. Okay, so that's not uniform. That's not what we want to say uniform. So, and in the example, right after the definition of uniform convergence, we modify it a little bit. We know that once it is less than Z0, ops value of Z0, it always converges. That is point-wise. This is point-wise. For every point, you can realize it, but it depends on this point. And now we have the same series, and we require this Z less than or equal to R less than ops value of Z0. Okay, it's not it cannot be as close as possible to Z0. There is a little gap between them. With this gap, you see here, we can replace Z by R and use R to get the capital N. We use R to have, let's make it more formal. Okay, so given epsilon greater than 0, there exists a capital N depend on R, depend on epsilon, such that for n greater than capital N, R over Z0 ups value to power n plus 1 less than epsilon. Okay, it is less than epsilon. So the Z over Z0 to n plus 1 is also less than epsilon for all Z less than R, less than or equal to R, less than or equal to less than Z0. The closed disk, we're talking about the closed disk. Here is the open disk. Okay, then this is a uniform. This is a uniform. So the limit, you see here, the limit depend on R but not depend on Z. So the limit Z over Z0 and plus 1 equal to 0 is uniform on the closed disk with centered at 0 with radius R. This is at R. And then you have the this one. This is in the partial sum. When you have a partial sum uniformly convergent, then the series is uniformly convergent. The series is uniformly convergent. Okay, so let me make it clear. Sigma Z over Z0 to J's power, J from 0 to infinity, 2 branches, converges over the open disk centered at 0 with the radius ups value of Z0. Uniformly converges over this closed disk. Here this R is less than Z0, whatever, closed disk. Okay, so this is the first section. The first section is very standard. You may see this section in this textbook or in that textbook, even in the calculus. So, but we still need to present it because we want to set up the terminology, and we also just recall what we need. We have a comparison test, we have a ratio test, a geometric series, and stuff, and uniform convergence. Okay, so the section 5.2, we are going to apply the general theory to our series representation. The 5.2 is a Taylor series. Taylor series. First, let's see the definition. The definition: if you have F is analytic at a point Z0, then the series F Z0, F prime of Z0, Z minus Z0, F double prime of Z0 over 2 factorial Z minus Z0 squared, and infinite series. This is an infinite series of functions, and the general term is like the J's derivative evaluated at Z0 over J factorial times Z minus Z0 to J's power. J is from 0 to infinity, including the constant term. And this is a series attached to this analytic function, and this series is called the Taylor series. for f around z0. Okay, so we just claim you attach it something, but we don't say it is equal so far. So when this z0 is equal to 0, when there's no z0, just z to j, it is also called Maclaurin series for z0. Okay, so that's a Taylor series and Maclaurin series. Maclaurin series is just a special series when you choose a center. Z0 is called the center. Okay, the center. Choose center as origin, and when you check here, if you have a polynomial, for example, if you have a polynomial, let's just pick up the simplest polynomial, x squared plus 2x plus 1. Let's try to check its Maclaurin series. Maclaurin series, this is Maclaurin series, sigma j from 0 to infinity, j's derivative at 0 over j factorial z to j. You need the first the evaluation at 0. The evaluation at 0 is 1. So j0 is 1. And the derivative f prime of x is 2x plus 2. The derivative evaluated at 0 is 2. So f first derivative evaluated at 0 is 2. What is, it's a 2. It's 2 over 1 factorial. 1 factorial is still 2. And f double prime evaluated at 0. F double prime is 2. So this is 2. So f double prime evaluated at 0 over 2 factorial is 2 over 2 factorial is 1. So, and whatever other derivative are always 0. You want to differentiate, just have 0. So in this case, for the polynomial, the Maclaurin series is a finite sum. And let's check it. So the first term is 1. The linear term is 2. The square term is x squared. So you see here the Maclaurin series recover the original function. That's all. This is not the special case. This is a general case. Whenever you have a polynomial, it is always equal to its power series. It's j z0, j factorial, z minus z0 to j from 0 to infinity. And for the polynomial, Pn is a polynomial. Of degree n. For the polynomial, this Taylor series is a finite sum.